and gentlemen, this is the third of our distinguished speakers' talks. We're fortunate to have Donald Geman of the University of Massachusetts, and soon of Johns Hopkins. And he's a famous person working on image processing and simulated annealing. There's a very famous paper by him and his brother. I don't know its title, but that's where we learned the procedure from. And he's going to talk about a stochastic feedback model for image retrieval.
Thank you, Fred. Well, thank you for inviting me to this seminar series. I just learned this morning all about this workshop. Very impressive format, these 4 groups, etc. I hope I have something to say that will be of interest to the people attending the workshop. I understand that it's not exactly square in any of these 4 themes, but maybe it's close enough that there could be some interest. This work was done, at least initiated, during a stage. This was like an internship of 2 students from École Polytechnique in France who came to the University of Massachusetts in the spring of 1998 to finish their studies at École Polytechnique by doing this scientific internship at the University of Massachusetts. And that winter I was thinking, what on earth could they do? I never supervised something quite like this. These are very, very good students, by the way. And so I had this idea that perhaps they could look at this image retrieval problem. I knew nothing about this problem. So we began by reading some papers together. And I found one paper in particular that I liked, that I thought stood out from the literature. It was a paper by a group at NEC. I'll come back to the paper later on. The first author is Cox, but there's 6 or 7 authors. And they had what they called a Bayesian approach to image retrieval. They had a system they had developed called the Pick Hunter image retrieval system. And I thought it had some rough edges, to be sure, and some soft spots scientifically. But on the whole, I thought they were on a good track. And it was a very coherent way to look at the problem. So that was our starting point. And again, I'll come back to that paper because I want to give it full credit. And so these 2 fellows, Roland Moquet and Mathieu Tisserand, did this piece of work and then disappeared. I mean, Roland disappeared into the Ukraine for a year on some strange project, and Mathieu disappeared in California somewhere. This was not followed up as a PhD dissertation. And then I followed up the work a little bit at INRIA. So that's how it began. And the only written form of this work is a proceedings paper in a conference in France last winter. I keep meaning to write it up. I'm pretty slow about writing things up. You can probably see from the handwritten transparencies that I maybe haven't entirely entered the new age. So here's the problem. Imagine a pretty large database of images, and you, the user, let us say, have an image in your mind that, let's, for simplicity, assume is in the database. I mean, there are all kinds of variations of this problem, but I want to take what I think is one of the simplest variations, one of the most concrete. So there's this very large database of images, and you have an image in your mind. You see it in your mind's eye. Now, of course, in many cases, you would have other information. Let's say it's a painting. You might know the name of the painter or something of this nature, or it's an image in a medical archive, and you might remember something, of course, more specific about it than just seeing the image in your mind. But I want to, just for the moment, I want to keep the text issue aside, the annotation by semantical content. I'll come back to it a little bit later. But right now, all you know is that you see it in your mind's eye, and you know it's in the database. And we want to find a civilized way of presenting that image to you on the screen. So what do I mean by a civilized way? I want to think of a user who has no experience whatsoever with images, doesn't even know what a digital image is, what a feature is, doesn't have any idea of how images are indexed or stored and so forth and so on. So I want to just imagine just an entirely ignorant user in the sense of not knowing anything about digital imagery, okay? So the most we want to ask of this person is to make some choices based on whatever mechanism this person wishes to use. I mean, this person doesn't know what a metric is, so it's just going to make some choices. So for example, one example of what I would call a civilized procedure would be the following. Now, imagine this is, just to make this very concrete, imagine this is my database. So there's only 16 images in the database. Really, of course, I want to think about a scenario in which there's, say, 16,000 order of magnitude, not 16. But imagine this is the database. And imagine, let me just pick one at random, this one, that's your image. You know, you see that tile in your mind, and there it is in the database. Now, you want to be shown that image on the computer screen. So an example of a civilized procedure is that I'm going to pick two of these, I don't know, this one, and show you these two, and you're going to say the image you have in your mind, namely this one, is closer to the left or to the right. So the only input you provide as the user is to click left or right. And you're using some method of comparing that is entirely your own. It's entirely subjective. So one of the themes of this talk is going to be about modeling human subjectivity. How do we do that? So I show you these two. And let's say you say it's closer to this one. Now I pick two other ones, this one and this one. And I show you these two. And again, you make a decision. It's closer to the left or the right. And the idea is in the fewest number of queries, in the fewest number of iterations, on average, everything will be an expected value, put up the images, one of the two displayed ones. Now, presumably, as soon as your image is among the two that are displayed, you say, oh, that's it. There's a third option which says, we're done, it's the one on the left. Okay? So that's an example of a civilized procedure as long as the number of queries is relatively small, the expected number. People just aren't going to put up with a sequence of queries that has mean 18 or something. Nobody's going to go through this thing 18 times to see their image. They're going to get frustrated, bored, they're going to do something else. So we really need to find a way to do this with on the order of 10 to 15 queries at maximum. Now, of course, it may not be possible to stay within the framework of only displaying 2 images. Maybe eventually we're going to have to display 4 images or 8 images and ask the user to pick out those which are closest to the image he has in mind. So there are many, many possible generalizations of this very simplistic scenario of just putting up 2 images and asking the user to declare left or right. But let's stick with that because it's so concrete and simple. Let's see how far we can go with this very, very simple scenario. So a little bit of notation now. Here's my image database. I'll just write I1 up to IN for the images in the database. And now I'm going to assume that this database is annotated in the following way. That each image in the database is assigned a feature vector whose components are themselves vectors and which capture what are called low-level image attributes, such as histograms of edge orientations, histograms involving Fourier coefficients, histograms involving color components, things of this nature. Notice that I'm talking about just histograms of statistics of the image that do not involve interpretation or semantical content. Now, ideally, what we would like to do is annotate the images in the database by their semantical content, so that along with each image is perhaps a caption or at least a set of keywords that describe the image in symbolic or semantical terms. You know, a small house on a prairie with mountains in the background, a stream in the foreground, whatever. But that's an unsolved problem in computer vision. Nobody knows how to take a database of images, run it through some computer vision system, and come out with a semantical description, even a set of keywords. I mean, that's, I think, almost everybody would agree that's an unsolved problem. So that many of these image databases, nearly all of them, are not annotated in a semantical fashion. Now, if they were, of course, we could do a much better job of this. We could use the keywords to bias, for example, a prior distribution on the images of the database. In other words, if the user were to supply keywords, obviously we could do a lot better than anything I'm going to show you. And again, we can come back to this a little later during the discussion or whatever about how exactly you could weave into the framework I'm going to present indices that have semantic content. But for now, let's assume they're only these low-level image attributes. Now, also, I want to have a family of metrics. This is very, very important. The heart of this approach is the concept of a random metric. The idea that the metric is a random variable itself that's being used to make the decision. So let's imagine that I have a family, there's some TV ad that has a fly. Let's imagine that I have a family of metrics indexed as follows. For each of the features, for example, for the color feature, there's an appropriate metric that measures the distance between two images based on their colors. And then similarly, I have some other metric that is dedicated to a difference between two images based on their edge statistics, and another for Fourier and so forth and so on. So I'm just going to collect all these into one big metric between images, and what I'm going to allow to vary are the coefficients, the alpha j's, how much I weight these different attributes in my overall metric. So later I'm going to talk about adjusting these alpha j's dynamically online in a way that depends on both the target and the two that are displayed. Because ultimately what I'm aiming at is a display-dependent, target-dependent metric, because that's what people do. I am going to demonstrate to you in a series of simulations that indeed that is what people do. The metric people use, now this may just, you may say, well, that's self-evident, it's obvious. The metric that people use to make a declaration, whether the image they have in their mind is closer to the left or right of two displayed images, will generally depend on what those two displayed images are and on how they interact with the image in mind. That, what I think is sort of self-evident property of decision making, had not hitherto appeared in work in image retrieval, to my knowledge at least. And again, I don't have the same command literature I do of some of the things I've worked on for a longer period of time, but to my knowledge that had not been done. So that's my family of metrics. Now, I'm going to stick with this very simple system of only two displayed images. So here are I can enumerate all the queries now. For every pair of images in the database, and for every possible metric, i.e. specification of the constants alpha 1 to whatever it was, and for every possible target, there is then a function, a value, a 0 or a 1, x sub I j di. This returns the answer 1 if, let us say, the left image is closer to the target under the metric d, and the value 0 otherwise, if the right image is closer under the metric d. So this gives me a family of queries indexed by pairs of images, metrics, and targets. Now I want to come back for a moment to the motivation for this work. The motivation for this work was the work of Cox and a number of other people at several institutions. I've read more carefully yesterday evening the footnotes on the names in the paper, and they were from the NEC Corporation, but also from some other institutions, AT&T and other places. They, starting around 1996, they published a sequence of papers in conference proceedings and here and there, culminating in a paper that recently appeared in IEEE Transactions Image Processing on the Pick Hunter image retrieval system. And the core of this image retrieval system, again, is what they call target search. So there's one image in the mind of the user, and what they also call comparison search, just making comparisons among displayed images. And they take a Bayesian point of view. That is to say, they assume there's a prior distribution on the images in the database. The weights in the prior reflect your a priori belief that that image is in the mind of the user. So without any other evidence, it's flat. And then it involves an observation model in some sense for the likelihood that you would get a certain answer given the history of queries and given what the true image is, a conditional distribution for how you would respond given what's been displayed already, what's been answered already, and what you have in mind. Now, all of that struck me as very sensible, but what did not strike me as sensible or realistic was that one single metric was fixed in advance, one of these small d's, and it was assumed that this was the metric that was being used to answer the queries, independently of the user, independently of the display, independently of the target. And that this metric was being used, and that what you observed was a kind of fuzzy sigmoidal version of the answer based only on the distance, on the difference of distances. Look at the distance from target to display left. Look at the distance from target to display right under this one fixed metric. Look at the difference of those two distances. And then only based on that, just within a sigmoid type scenario, the user will respond left or right. I didn't like the idea that there was this metric in the background that was being used, that was driving everything. It didn't seem realistic. So our starting point, in a way, was to imagine that the metrics were random variables. And these are random variables with values in the space of metrics. And Dij, capital Dij, to indicate a random variable, determines the answer to the display when I and j are displayed. Determines the answer, 0 or 1, when I and j are displayed. Now, here's the statistical model, and then I'll try to give you a behavioral interpretation of this model in a moment. Let me just, in a cold way, lay out the statistical model. It's very compact. And then I'll kind of justify it in terms of people and populations and so forth. So here's the model that we have. First, we assume that if the target image is I sub L, the probability that the metric little d is used when the display is I and j is given by some distribution, not necessarily a point mass. In other words, we're not fixing one. It's a true distribution on metrics indexed by pairs and possible targets. So these are the one-dimensional distributions, the marginal distributions of these of this family of metric random variables. I'm giving you the conditional one-dimensional distributions of the Dij, conditional on the target. Now remember, up here I've also specified the prior distribution on the target variable. I also then make the assumption...
Target is what you're looking for.
Yes. The target's the one you have in your mind, and it's one of the images in the database. And it's what you hope to see shown to you on the screen.
And the subscript IL, that's not the subscripts we had before.
It is. It's a pair of images. It refers to I sub I and I sub L or I sub J. I of L refer to a pair of images.
But normally I star would not be IL, right?
I star just denotes the random variable. It's one of the images in the database.
Oh, not the one you have in mind.
It is the one you have in mind, yeah. I star is the one you have in mind. It's a random variable. It has some prior distribution. And I'm giving you the conditional distribution that the metric being used to answer the question is little d, conditional on the two being displayed being I and j, and the true one being I sub L.
All right. So everything, even the thing that you have in mind, is actually in the data.
Yes. Yes. Yes, we're making that assumption to simplify the problem, that it's in the set. We can then talk, there are many generalizations of this, so-called category search and free browsing and so forth and so on, but I'm fixing this very concrete variation. Now, notice that once I've determined these distributions, capital Xij, let me define capital Xij to be little xij. Remember, that was the query where you plug in capital Dij and I star. So that becomes a random variable, capital Xij. Notice now that once I've specified the one-dimensional conditional distributions, the marginal distribution on I star, and I've made the conditional independence hypothesis, the whole system is determined stochastically. So obviously, I just want to point out that the joint distribution of this triple is now determined. So in principle, I can, once I know the mu's of IJLs and P0, the prior, I can compute any quantity relative to this stochastic system of targets, metrics, and queries.
Say again what X is.
Xij is a binary random variable returning 0 or 1. It returns 1 if, well, when evaluated at target I star, and when evaluated at metric capital Dij, it returns the value 1 if the left image is closer to I star than the right image is under the metric capital Dij.
So that's the decision rule.
Right. That's how the answer is. That's the model for how the answer is provided. It's kind of a little complicated because there's a number of things floating around. There's the metric and the target and the pair, but everything is right in here. Everything is here. Now, let me try to explain this in sort of behavioral terms. Some people see it in an easier way. So, you know, as a probabilist, there's usually this capital omega somewhere. And usually I laugh at that, like all other probabilists, you know, the omega and the sigma field. I mean, I haven't thought about a sigma field in 20 years, but you know, I had a period of my life in the 70s when I was doing more classical probability, stochastic processes, mainstream probability theory. That's my background, is in stochastic processes. But then at some point I even got rid of the omega, which I figured this is going too far. You know, I got to come back to the omega. So I started asking myself, well, what would be the omega here? I mean, what's the appropriate sample space in this? And the appropriate sample space, I think, simply is people. So each little omega, imagine, is an individual. And there's as many of these as people on the planet. So that's my big probability space. So what's I of omega? Well, that's easy. I star of omega. I'm assuming every person on the planet has an image in their mind they want to find in this database. Why not? Okay? So I star of omega is the target image for person omega. What is Dij? Well, these are the metrics that are used by person omega if the display pair is I and j. So we're assuming that if I show any one of you a display, and if you have a target, you will use a certain metric, and if I show you the same display later on, and you have the same target, you'll use the same metric. That's what I'm assuming, that your metric is just fixed once the display and the target are fixed. And then these are the answers, the Xij are the answers provided by person omega. So that's one way to kind of think about all this in very, very simple terms. Now, equivalently, and all of these are just ways of paraphrasing the same thing. Equivalently, if the target image is I sub L, and given I sub I and I sub j are displayed, the user chooses a metric via muijl and responds little xij to the question, is the target closer to the left or to the right? I mean, these are all equivalent ways of saying this. So what is the prior distribution? It's just the fraction of people. The prior mass on image I sub L is just the fraction of people who have that image in their mind divided by the total number of people, and so forth and so on. Everything, all the quantities I talked about will have relative frequency interpretations. This helps some people. That's just trying to make the stochastic framework as clear as possible. Now, how do we decide what to display? The guts of this thing is that the computer program we're going to write is going to make a decision on what two images to display driven by the desire to minimize the expected number of queries until the target is found. Found meaning displayed. So let me let I sub k and j sub k be the pair displayed at step k. So we have step 0, step 1, 2, 3, 4, etc. That's the pair of images displayed at step k. And let me let little x1 up to little xk be the first k answers. So these are just binary. These are zeros and ones. And then I'll write bk for the querying history. So bk represents, really bk is the set of queries, all the pairs of images that were displayed and their answers. But let me just think of it as an event in the probability space. X sub I sub 1, j sub 1 was answered little x sub 1. Query capital X I1 j1 gave the answer little x1 up to the kth one. So this is the history of what's happened so far. Okay? And it's an event in my probability space. Now here's the basic idea. The basic idea is that we're going to determine the pair of images based on maximizing information gain as measured by Shannon entropy. So what are we going to do? We're going to pick, conditional on what we've done so far, we're going to pick that pair of images which most reduces the entropy of I star, conditional on what we've already observed, and in the sense of a random variable now, conditional on that new query. So in mathematical language, I1, J1, the first pair of displayed images, minimizes the conditional entropy of I star given capital X sub ij. So you run over all possible pairs ij, and you take the one that minimizes that entropy. Now, remember that this system is well-defined stochastically, so this is a well-defined number for each ij. Now, equivalently, what we're doing is we're maximizing the mutual information between xij and I star, if you prefer to think of it that way. Now, what about at step k, or k plus 1? What is the mechanism for choosing the two displayed images? At step k plus 1, it's just about the same thing, except everything is conditional on bk. So all your probability measures are all the conditional distributions conditioned on bk, and then I do the same thing. To the greatest extent possible, I reduce the uncertainty as measured by the entropy of the target, conditional on bk. Of course, bk is, this is an event, this is a random variable, but in fact, oh yes. For those of you that may have not looked at entropy for a while or never looked at entropy, let me just digress for a few seconds and remind you of the definition of entropy so that you'll get a better feeling for what all this is about. I apologize to those who've been working with entropy for years and years and years. How do you measure uncertainty in mathematical terms? Again, this is just a little mini tutorial, okay, just to make sure we're all on the same page, so to speak. Let's suppose I have random variables u and v, and I have an event b. And p will just denote a distribution identified by context. It's going to be the distribution of u or v or something else. What is the entropy of v? What's the definition of the entropy of v? It's minus expected value log p of v, the distribution evaluated at capital V, and there it is. It's just the sum of p of v log p of v, standard Shannon entropy. Logs, let's say, are base 2. So that's the definition of the entropy of a random variable. What about if you condition on an event, as we did to choose the first two queries? Remember, we conditioned on, no we did, later on to pick the k plus first, we conditioned on an event involving the first k queries. Well, you just use the conditional probability measure in place of the absolute measure. And what does it mean to condition on, to talk about conditional entropy of V given an event and a random variable? Well, there's the definition. It's just a very natural thing. We just average over the conditional distribution of the random variable we're conditioning on. And we get conditional entropy given an event and a random variable. Now, in everything I'm going to talk about, you could replace Shannon entropy by some other divergence measure. If you don't like Shannon entropy for computational or other reasons, you can use the Hellinger distance or others. It just doesn't matter. Clearly, you just want an entropy-like quantity, something which is maximized on the uniform distribution, minimized on a point mass, and has some decent properties in between, concavity or something. Okay, that was just this mini tutorial on measuring uncertainty. I want to jump right away to a little mini experiment just to give you an idea of how this works. I want to compare what happens if we use entropy reduction as our driving principle and something much simpler. Here's something much simpler. After k queries, it's easy to update the posterior distribution on targets, given what you've seen so far. I'm going to show you a formula for that in a few minutes. But certainly imagine we start with the prior. That's why I called it P0. Nothing had happened yet. Then P sub 1, P sub 2 is a sequence of distributions on the database, representing the probability distribution of each of those being the target, given what's been observed so far. Now this posterior evolves, and hopefully becomes more and more peaked as more information is garnered from the user. Now, I want to show you how this thing peaks. I want to give you a graphical illustration of the peaking of the posterior under two regimes. One regime is picking the display based on reducing entropy, and the other is just picking the top two most likely targets at stage k plus 1, based on the first k. Just make that the display. Just pick the top two and put them up. Now, you have to really think about this. I mean, that sounds great in a way. Put the top two up. I mean, why not? I mean, those are your single best guesses, the top two modes, two most likely images under the posterior. But that's not what divide and conquer is about. When we play 20 questions, we ask questions like dead or alive. We don't go for a specific person. We try to divide the space of hypotheses in two vis-a-vis the current distribution. We do our best to divide it in two. That's divide and conquer, not go for the two most likely. Well, here's one experiment where there's only 100 images. Yes, Mike?
I'm glad you just brought this up because I was going to ask you when you had the conditional entropy. If you go back to that slide with H and you replace it with, rather than the expectation of the conditional, which is what H is, you replace it with log P, so you can maximize or minimize log P.
Here you're talking about? Or?
Well, even in the slide before you start off with H of V.
Oh, yes. Okay.
You brought up Hellinger distance and various things, and I was sitting there thinking, okay, what would be the map? Yeah, so instead of H, I want to relate to what you just said about what if we pulled the most likely. So instead of H, let's put something there that's not an expectation over the conditional, but just is log P itself and probably be max and then min or something.
Exactly.
And that would correspond to choosing the two, that would correspond to the scenario you just described, which is choosing the two most likely given what you know.
Not exactly. Well, yeah, it would if I just replace the whole thing. So if I just take this out altogether, put a max here, and put here probability of I star equals, let's say, I sub j, and just maximize, just take the two most likely images under the posterior, under the conditional probability on targets given BK. That's right. That would be another possibility.
So that would be like the map. Is there a way to think of that?
Yeah, that's right. It's the map and the next one.
Okay.
Exactly.
So then what I wanted to do was help me to understand why going to this, an entropy function, or you related to Hellinger and you said you need certain basic properties. How does that avoid the quandary of being greedy and not splitting, where map doesn't? You see what I'm,
Uh-huh.
you just argued that in 20 questions, we're not greedy and go to maximize or something, but we do, rather we split. We
Right.
the uncertainty, and that has to do with your entropy criteria.
Right.
So it's clear to you why maximizing customary probability doesn't do the splitting, and this does, and it's not clear to me. And maybe we can talk about it in discussion, but I wanted you to add a little more, just for me to get that.
Well, a very dramatic example of these two philosophies was in an algorithm I talked about here, I think before, about tracking roads, where you go and you implement a little local filter to decide whether or not the road passes through that location in an image. These were satellite images and 10-meter resolution satellite images, and they have superhighways in them, and we wanted to track the highways. And we used an entropy reduction mechanism to decide where to look next, to solve the where to look next problem. Where do you go evaluate a local filter to see if the road went through there or not? Of course, it's a fuzzy answer. It just gives an answer. It's not, you can never know locally whether the road will. You just get an answer when the small values indicate it's unlikely the road passes through there, large values that it's likely. Now, in that framework, you can imagine two philosophies. One is go to the location which is most likely under the current distribution on roads to be a place you haven't examined in yet and which is on the road. That's the map one. Another philosophy is go to the location which has the property that it divides, well, go to that it most reduces the uncertainty about the distribution on roads given you make that observation now. Another way of saying it in a simple framework is that it divides the set of roads into two halves. And the second one is immeasurably more powerful. I mean, it's not just immeasurably more powerful than the first. That's another version of the same thing you're saying. You don't want to go to the place that is the most likely to be on the road because you don't learn very much. Just as you don't learn very much by going to a place that is the least likely, you learn the most by going to a place that is right in the middle somewhere. Now, in the middle somewhere, it's not quite 50-50. It's somewhere between 0.4 and 0.6, depending on the statistics of the problem. That's another subject, a little complex, but that's a variation of the same thing. And there's in those kinds of scenarios, there's a dramatic difference between the two. Now, why? It's a complex question about, but. So let me come back to this example to look at the peaking now. So I have 100 images in the database. And what we're going to see is, at step one, we see the uniform distribution on these 100 images. Now on the left here, along this side, you're going to see the evolving posterior distribution under entropy. And on the right, you're going to see the evolving posterior distribution under picking the top two modes, the map and the next map. So you see that there's not that much difference after one query, after two queries, after three queries, after four queries. So what has happened here? Well, after four queries, we're pretty much down to three candidates with entropy criteria, whereas with picking the top two, we're still pretty fuzzy. So, and that's the kind of thing we observed, that if you stay with this 20 questions with divide and conquer as expressed by entropy minimization, you peak much faster than if you do the computationally simpler thing, by the way, of just picking the top two modes. Now, I haven't, what this experiment pertains to, I'll show you in just a minute where this came from. What about computation? I have to say something about computation. How do you compute this? What's involved, if you were to code this, what's involved in this entropy business? Now, there's a loop over all pairs of images, so just put that aside. The fundamental thing we have to compute is the conditional entropy. How do we compute the conditional entropy? I want to say something about that. So, unfortunately, I have to define this set that plays a crucial role. If I display I and j, and if the target is L, this is the set of, you've got to flip your reasoning around. This is the set of metrics that would produce the answer 1. These are all the metrics that would lead you to answer left if I display ij and the true target is L. And then I'll use this notation: to the first power is the set, to the 0 power is the complement. So here's the posterior. It's very easy to write down the posterior. It's just a standard calculation. Many of you have been through it and worked in a Bayesian framework. And just notice that at the end of the day, the posterior only depends, and it can only depend, what else is there, on the posterior distribution. I'm sorry, it's not the posterior. The conditional distribution for the history, given the target, only depends on these mu sub ijls. And because of conditional independence, you have the product here. So this gives you the probability of observing a given history, given the image you have in your mind is I sub L. And then from this, if you just plug this in, this together with P0, the prior, determines the posterior. So at the end of the day, the posterior is of course determined by the mu's and P0. And there's an explicit formula for it. So what you're going to do is you're going to display two images, you're going to compute the posterior, you're going to use the posterior to decide what two images to display next, recompute the posterior, and operate cyclically in that fashion. Now what about the entropy itself? I want to make sure you understand this. How do I compute the conditional entropy? Well, to compute the conditional entropy, I need this. If you go back to my transparency on entropy, I do need to be able to compute, this is the conditional entropy of I star given bk and given xij equals little x, that particular value. This whole expression would be the conditional entropy of I star given bk and given just xij. Well, I can compute this because I can easily compute this probability. This is the probability I respond little x given I have history bk. Notice that it's just this weighted average of these metrics, of these distributions mu, weighted with the posterior. And I compute, so that's this piece right here. And now I need to compute this, I need this piece. And I get that as simply a ratio. I'm not going into details here, and I'm going through this much too quickly for anybody to read it line by line and absorb it. But I just wanted to give you an idea of the complexity of the computations. It's nothing. I mean, once you get on top of this kind of thing, you code in an afternoon. Okay? Now, the way we actually do it, I don't have time to talk about this today. I had to sacrifice something, so I decided to sacrifice Monte Carlo estimation. There's a lot of Monte Carlo stuff going around to avoid actually looping over pairs, to avoid, you can make all this 2 orders of magnitude faster by some tricks and whatnot, where you just estimate things, and it works fine. And I'm just sweeping that under the rug, and I'm not going to say any more about it. But there's a Monte Carlo component to the whole thing to avoid doing all the calculations on the head. So let's go to experiments. I'm going to show you a succession of models of increasing complexity. The models are of increasing complexity vis-a-vis the complexity of that distribution mu sub ijl. Because that's all I have to control now. P0 is uniform. So here's the first model. The first model, and then I'm going to summarize, we're going to see how well we do with these 4 models. The first model is that there's one fixed metric known to the user and known to the system, and this is the only metric that's involved in the story. So these mu ijl are point masses. So this metric d star is always being used to answer the queries. And the person who's designing the system, in other words, programming this to display 2 images, knows that metric that the user is using. Now in this case, the only source of randomness in the system is the unknown target. This then determines the answers to the queries, and hence the conditional distribution of any history is just 0 or 1. It's 1 if it's consistent with this metric and this sequence of answers, 0 otherwise. Consequently, the entropy, well, this entropy divides into 2 pieces. The entropy, the uncertainty about I star given the history, minus the amount of uncertainty in the query given vk. This is not a function of ij. Remember, we're looping over ij to take the min. So minimizing entropy is equivalent to maximizing the entropy of xij. But xij is a binary random variable. How do you maximize the entropy of a binary random variable? 50-50. Right? So all you're doing is dividing the database as evenly as possible under the current posterior. You're just finding that pair of images in display that would, in terms of the answers, split the database into 2 pieces of as equal of mass as possible under the posterior. That's what you're doing in this very, very simple baseline case. There's no uncertainty other than the target. Now, in this very, very simple case, where we have the least amount of uncertainty in the system, this is our optimal performance. You're never going to do better than that. You're never going to do better than knowing what metric the person is using. So this gives us a baseline. So what's the baseline? Well, you can actually compute the expected number of queries you need to get the target in this baseline case. And it's basically what you think. It's log n, but there's a -2. The reason there's a -2 is because the reason this actually violates the basic bound of information theory, that the expected length of the code is bigger than the entropy, is that because you're declaring which one, if you see your target, you're saying it's there. So that accounts for that -2 in this. But basically, log n is your optimal performance. Now, you can do an experiment in this case. It's very simple to actually do an experiment. No surprise. So this is a synthetic experiment. I'm going to show you a synthetic experiment and a real experiment. A real experiment involves people answering questions. The synthetic experiment is that the images are just points in a Euclidean space. So that's the synthetic experiment. And the metric is Euclidean metric. So here's the curve, the optimal curve, and sure enough, in huge simulations, which take no time at all, as a function of the database size, in all my illustrations, the vertical axis is the average number of queries, and the horizontal axis is the size of the database. So here's this optimal curve, log base 2 minus n, and sure enough, you achieve it. Of course. So again, this is the synthetic database, computer answers, computers are providing the answers, and the metric is known. So that's our baseline case.
Don, I don't think I understand this, but I'm so close, so I want to.
All right, let's see if we can close the gap.
Right, we have points in Rn, we use the Euclidean metric,
Yeah.
and we want to bring up 2 points in Rn that after we know the answer of which is closer to which, something's happened to the posterior probability that it's now split on something. But I don't see it yet. What's being split? What's being split? I don't see it.
Well, okay. I have all these points, a cloud of points in Euclidean space. One of them is the one I have in mind.
Okay.
Now, and I have some metric. Now, I want to display, in some sense, pick 2 of these points and ask you, is your point closer to this one or this one?
Yeah.
And I want to do it in such a way that on the order of half the points will respond, half the cloud of points will say they're closer to the left, and half will say they're closer to the right. And that will give me a divide and conquer. Now I know the other half are out because everything's deterministic at this point. There's no randomness in the metric. So I'm down to half the points. Now I want to divide those in half, and all I'm doing is a dichotomous search down to the point.
So it's just like a vector quantization implementation?
Yeah. Yeah, there's nothing, that's why I call it the baseline case. It's very elementary. I'm just narrowing down these points until I have it. Now, in this very simple case, the posterior is just uniform on the active hypotheses. right? Half of them die, get zero mass under the posterior, and the other half are just uniformly weighted. Now, it may not be exactly half because I don't know that I can find a pair to display that will really divide in half, but I come as close as possible. So that's all that's going on in this baseline case. Does that help at all? Let's go to the next model now. The next simplest possible model. The next simplest possible model is that, actually it violates my conditional independence assumption, but picky. I want to throw it in anyway. Right? The next simplest possible model is that the same metric is used every time, but it's a random variable. It's not a constant. So that these distributions are all, they're not point masses, but they're all the same. They're independent of the display and independent of the target. So there's just one fixed distribution. The first model was one fixed metric. The second model is one fixed distribution. Okay, so that's the second model. Now, let's compare what happens in the first and second models. Now, can we predict? We should be able to predict. Let's again just take a synthetic case where the images are points in Rn. And let's, we go through this whole program, we compute the entropy, we solve the entropy minimization problem, we get a pair to display. What do you think is going to happen? We've added uncertainty to the system. We have to do worse, right? We've added some more uncertainty. And we do worse. So here is the, let's see, here's the baseline. This is the optimal. That's the log n minus 2 curve. Here is, trouble seeing this. Oh, it's much easier to see here. Something wrong here. I wrote, these are mislabeled. Okay. I jumped ahead once.
Excuse me, let's see if I understand. In the first case, we've picked a distance and fixed it. And therefore, it's clear this division, because if something is closer to this, the one that's further just can't be, so we divide. Now we're picking the distance at random.
Right.
But there is no reason why it should behave worse, because we could have started out picking a stupid distance. I mean,
well,
in the fixed case, the distance may have been completely inappropriate to the problem, and then a random distance should do better. So it's not true that it will always do worse.
In an average sense, it will.
Why is that?
Well, no, that's okay. Because in the first case, we were assuming the right answer, that this really was the metric. Oh, because of the space of metrics, you're saying.
Yeah,
I see.
They have a very bad metric, which hardly distinguishes anything.
Yeah, that's true. That's true. I'm thinking in an average sense over picking one out of the space of metrics and fixing it, but that's right. I have to come back. I have to backtrack just a bit because I realized that on my transparency, I have two experiments combined. Let me just go back to this for a second. Let me tell you what the third model is so we can compare the second and third. The third model is that I pick a new sample from this distribution each time. I don't fix it once and forever. Dij is not frozen at D. There's a subtle difference, an important difference. I pick IID, independent identically distributed metrics, from the distribution. I don't pick once at step 1 and then freeze the metric. So that's model 2 and model 3. So let me show you what happens in this case. Now this is the synthetic case again. Here, on the top is the IID case. And we do worse. We do worse than we do in the other case. With computer simulations, we do worse than in the case where the metric is picked from the distribution and frozen. And again, I would claim that that's intuitive. We should do worse. There's more uncertainty, so we pay for it. We pay for it in the fact that this curve lies above this curve, that the average number of responses is larger when there's an IID sequence. Let's go now before I come to the most general case, the most interesting one, let me show you some human experiments with human beings. So there's 2 series of experiments. The synthetic ones, we're finished with them. Now let's bring people into the story, and very soon I'll come to my punchline. Yes?
In the synthetic experiment where you had a fixed mu,
Yeah.
that you were sampling, there the choice doesn't depend on ij, right? It's still a completely random metric chosen.
Yeah, that's right. It does not depend on the display. That's right. That's very important. Here's the synthetic experiment. I mean, the real experiment. It's not a real image database, but it's a interface that we designed to start to get an idea of how people behave. They're not images, they're just shapes. So these are the things in the database. They're just polygons. And the polygons are characterized by 4 properties. They have a darkness, they have a size, just small to big. They called it flatness. I repeated it to 2 guys from Polytechnique. Okay, an elongation factor, how elongated they are. And they have a number of vertices. The polygons have 4 attributes. Now, of course, the user doesn't know, and this is all hidden to the user. The user doesn't have to know anything about these 4 attributes. The user is just going to pick a polygon. That's going to be the image the person has in mind, and then answer questions when 2 polygons are displayed, whether the polygon they have in their mind is closer to the left or to the right. So we made a user interface to play this game. Here's the user interface. So here's the target. It's displayed actually. And then 2 polygons are displayed, and you click on choice 1 or choice 2. That's it. Okay? And again, the user has no instructions whatsoever. Just pick the one you think in whatever way you wish is closer to your target. So these guys are very energetic, and they got people into the lab from all over the place. They practically cornered people in the town of Amherst, let alone the people that were already in the computer lab, faculty members in the department, people that were working in the department. I mean, they just bothered everybody to get them to come and play the game, to collect statistics on how people would respond. So what we can do now is we can do something interesting. We can go through the same models, but have people provide the answers, but have the system generate the display by the model. But people are providing the answers. Let's see what happens. So these are now human responses. So this is the polygon world. So again, here's the baseline. And now notice, you have to think back to the previous transparency, because something has switched.
Baseline for which this?
No, just that, it's just log base 2n minus 2. That's all, just that. Something has changed. Now, ignore this for a minute. This would be to compare the results to previous results. Just look at these 2. They flipped with people. The IID model, assuming that a new metric is picked each time from the distribution, this dumb distribution that doesn't take into account the display or the target, just that a new metric is chosen each time, all of a sudden does better than the model with less uncertainty, namely pick the metric from the distribution and phase it. Those 2 curves have flipped. So this is the beginning of a trend that keeps going in this way. Let's go on. I just want you to notice that these 2 have flipped with human experiments.
But Don, the distribution on metrics, who picked the set of metrics?
The system has some set of metrics and some distribution.
Okay, for
all hidden to the
color
user.
And all of that.
Yeah.
And then I get to use, okay, and this is related to each thing, they have an attribute,
Yeah, it's just some uniform, it just took those 4 attributes and it was a linear combination with some fixed coefficients. Exactly, exactly. Let's go to the most interesting case now, the most general model.
Excuse me, let me just see if I understand. What happened is that people were picking, right? And the system was picking the 2 things to decide between by choosing at random the distance, which would then determine which one to pick.
Yep.
And choosing it at random
Well, wait,
is better because presumably, I mean, maybe because people keep changing their mind. They don't.
no, not exactly, Fred. The people are making the decisions about which one is closer.
Yes, I understand,
But the system is deciding which 2 metrics to display
which to
by doing a computation
right.
that I showed you earlier, substituting into that computation this distribution on metrics.
Yes,
Because you're integrating out the metrics in a way.
right. I see. I thought that they would pick at random.
No, the system is never picking a metric. The system is deciding which 2 images to display
So the
based on a
distribution
model.
the distribution stays fixed
Yes,
on the metric. It's just an average over the.
exactly. It's an
Right.
average. You just, in some sense, you're integrating out over the space of metrics when you do those entropy computations. Now, here's the realistic case. Let's suppose you have a green circle in your brain, and I show you a blue circle and a black box. You're probably going to go for the blue circle because of shape. But if I show you a green square and a blue triangle, chances are you're going to go for the green square because of color, right? So the choice people really make depends on what they're shown and how it interacts with the image they have in their mind. And if we can bring that into the system, we ought to do better still. Now, how can we bring that into the system? The fact that the distribution should really depend on what's being shown as well as what the target is. Well, that's pretty easy, actually. I will show you our one and only attempt to bring it in. It worked just fine. Just remember that this is my space of metrics. Linear combinations on the individual attributes. Well, suppose that I just normalize it so the maximum distance between any 2 image and any attribute is 1. Now, here's one way to pick random coefficients. In other words, to generate a distribution on metrics. Look at the distance between for each triple, I, J, L again, look at how far I is from the target L in feature S, and compare that to how far it is from the other display in feature S. If that distance is large, pick the coefficient uniformly on 0 to that difference of distances. That's going to upweight attributes which have the property that the target is much closer to one or the other in that attribute. And if those distances are about the same, downweight those coefficients. That's going to tend to ignore attributes which have no discriminating power. Now notice this all depends on how these interact, all 3 interact, the target and the 2 displays. So that's one example of a mu that really depends on IJL, as opposed to just being some arbitrary distribution. Well, what happens when we take such a metric? Bingo. We do better still. The upper curve is, well, you have to compare it to the previous one, and it's hard to hold all these in your mind, and maybe it's not that important, it's only a detail, but we're now in here. We've done better. We've reduced the expected number of queries by allowing the distribution on metrics to be display and target dependent. So something interesting has happened, which we can summarize in this little picture. In the polygon world, here's a summary of what we've observed. The blue represent model simulations. As the models became more complex, from a fixed metric to a fixed distribution to IID fixed distribution to display and target dependent metrics, the performance in computer simulations degraded. In contrast, as the models became more complex, the performance with human beings improved. Now, because Roland disappeared into the Ukraine and Mathieu disappeared into California to do a PhD in something else, I never had the opportunity yet to kind of fill this in, to flesh this out. I'd love to see what happens with this metric. I mean, there are lots of other possibilities here to amplify this theme and to make it, to nail it down. And we're going to do that actually over the rest of this summer at INRIA with somebody else. But the trend is already there. Now it's very legitimate to ask what happens with real images. So all this was quite invigorating and fun, and we were all pretty high after this. And then we went to real image databases. And I have to say things changed. Things got much more difficult with real databases. The thing did not fall apart by any means. It gave expected response times that were quite as good as a system they had already developed over a number of years at INRIA in a project called Media. But it wasn't what I hoped for. It was clear there were some problems. For example, you have an image in your mind, and I show you two images at the beginning from a huge database. Your image is very unlike both of them. And so those first answers, there's a transition period where you need to get into the general category before this machinery takes hold and drives you toward the solution. So what you need to do is show more images at the beginning and get some idea of the category first. It's part of this, of a more, in a wider sense, a course-defined procedure. You have to get some sense of the category, and then this whole thing kicks in and drives you to the target image reasonably quickly. So that's one of a number of problems when you try to export this to real image databases. But we're going to be doing experiments over the next year with image databases, perhaps some medical image databases, certainly some of the painting databases that are available on the web, and other databases that have been collected at INRI in France. And I'm sorry for running over. Thank you. People have looked at that, I think. In fact, in the Pick Hunter paper that just came out that I alluded to at the beginning, they have a section on psychovisual, psychophysical experiments. And part of that is about trying to learn what people do, how people behave. People have begun to look at that question. It makes all the sense in the world. I'm not sure how to do it in a quantitative way, but certainly it's a sensible idea, without any doubt.
I mean, if you could look back across the path that people have chosen through the space, there would be some path that would be more consistent with certain strategies, if you had a strategy.
Right, that's right.
Rather than.
Right. In fact, they talk about a training period where they try to get some feeling for what users do. I think I don't remember the details because of the paper, that section of the paper, but I think it's very much along the lines of what you're talking about.
Certainly it's going to be different in a medical database than in an artist.
The medical scenario I have in mind, maybe it's unrealistic, is that, I don't know, I take a picture, I take an MR scan, and I see a lesion or something, and I say, gee, I've seen one like that before. You know, it's an unusual one. I say, gee, I've seen something like that. Where was it? You know, remember it was a couple of years ago. You can't remember the name of the patient, you know, but you've seen sort of one like it, and you'd like to see what happened in that case history. There are a number of scenarios like that that could be application.
You thought about training the muse?
Pardon?
After you have a sequence of real use physicians, have you thought of going back and trying to train the model of the muse?
No, we haven't. We have done nothing of that nature. No more global feedback. You know, we go all the way back. I mean, what we've done is really, in some ways, very superficial. We've just done some very preliminary things. We haven't, I guess, let me think now. Can you define the sequence of steps people go through when they start working on a problem? So you conceive something, you code it, you calibrate it, that you get into the ballpark for the parameters, and then you tweak, right? I mean, that's what people do in computer vision, at least, tweak the parameters. And I would say we never did the tweaking yet, nor did we go back to reconceive, which would be.
I can't remember if the mu was the distribution over the metrics. Is that right? No.
What?
I was wondering if you thought about trying to learn the distribution over the metrics.
Well, yeah, that's
exactly the mu. Okay, I
yeah.
couldn't remember what mu was.
Yeah, mu is a distribution on
Right.
metrics.
So I was thinking one way you could set up to get supervised training data for this would be to show the user 8 images, let's say, or some larger than 2, and say which one is the most like and which one is the least like. And
Right.
those are the ones you should have shown them, and that then would give you some training data that you could try to
Right, so you could
maximize
that's
likelihood.
right. So you would generate a training database, a labeled set of
Right.
where you have their decision would play the role of the supervised
Right.
labels, right. And then from that you could try to figure out what they're likely to do or what kind of decision making they're using.
Well,
Now-
you could just say, yeah, you would try to.
I wonder how user dependent
Maximize
that would be. I mean, when I started working this, they told me, you know, don't assume that there's some session with the person in advance. You're going to get right into it. They're going to be shown 2 images and make a decision. I mean, one of our thoughts at the beginning was, are we allowed to garner some information from this person one way or another, you know, in some preliminary session? And the advice I got from the people who run this team at INRIA was, better assume you jump right into it, but what you say makes a lot of sense, of course. You could maybe start to estimate that distribution.
Right.
Yeah.
And well, you're doing that now by picking, you know, you had the uniform, one of your experiments was uniform, the other one was based on this, I can't remember exactly the distance,
Yeah.
weighting certain characteristics
Right.
to the guess.
Right.
And you could get some kind of informed guess.
Right. Are they, somehow they're more driven by color than they are by whatever shape or whatever, yeah.
Have you thought about trying to incorporate any cognitive biases? So for example, when you put up the green circle, it kind of struck me that if you gave the person a blue circle and a green square, it's just my gut feeling, but I bet almost everyone would choose the blue circle because shape is far more of an important feature than color. Difficult you might get at in some sense, and distance, I'm sorry, because you may say the shapes are more distant for different
Yeah.
colors, but I'm not sure that's always going on.
So you think that, wait, you said the shape would dominate color in that case. Each of the display would have one part in common with the
Right.
target, and you're saying that shape would dominate color.
Right. Just my gut feeling, but I think there may be real cognitive biases.
Uh-huh. Well, no, we certainly haven't done that, no. But if those biases exist, it'd be a shame not to incorporate them.
Is there anything you can do to use this to see what sort of metrics are worth developing? I would think that you could look to see which metrics haven't been used much, haven't gotten much pass on. But it would be interesting if it's not too workload
So are you talking about actually the attributes?
We're talking about the attributes.
You know, what attributes would be, yeah.
And the way in which you compute distance on
Yeah.
those attributes.
Well, again, it makes sense. I don't know exactly how to carry it out, but no, we certainly haven't done anything like that. I mean, I probably told you more than I know already.
Don, I don't understand the problem of if I have an image and I have your setup. And let me tell you why I don't understand that problem. So like you said, medical imaging, but just think, I have an image now. I don't have a picture now, but I have an image. And I have your setup. I don't understand the problem because in your setup, you assume that you have this data vector of features.
Yeah.
Now, if I have an image, don't I just, if I've already decided on that database of features, the vector.
You don't have the image
No,
layer.
I know, in your problem, but, so now I want to change, I want to ask about, suppose I have the image retrieval problem of, I have an image, a digital image, not a picture in my mind, but I have a digital image. And now I want to think about how it relates to your system. So you said, I see a digital image of a lesion, and that means I have the digital image. I don't just have a picture of my body. I have a digital image. I don't see how it relates to your system. And the reason is, I'm confused about this, is because in your system, you're assuming that the whole database has this vector of attributes that are being calculated. Well, that means you decide on ways I could compute that vector of attributes on the image I have. Now, if I could compute the vector of attributes on the image I have, then I think what one then just does is chooses in the database or finds in the database then those that are closest using.
Sure.
You know,
If you
yeah.
have,
So you see what I'm asking?
if you have two things, that's a little different scenario. You're talking about I have a concrete image,
I really have.
and then I have one in my mind that this image reminds me of that I know is in the database. So you're saying just go compute your vector of attributes for the image you have in hand. You have an actual digital representation,
consistent
and
with
do a
your
nearest
database.
neighbor search or something.
Yeah.
Sure. Now that's surprisingly that's not so simple, by the way. That's not going to necessarily come up at all with the one you think.
Okay.
But it's a slightly different scenario. I was imagining we're not going to use that image at all that we have in hand. We're just going to play this game with the image in mind. I mean, in the usual scenario, you don't have actually an image in hand. You just have one in your mind's eye.
Is there a problem where this methodology is powerful that you're using, and you have an image? You know, you have grandma's picture,
Yeah.
and now you have a catalog of 2 million grandma pictures, and you want to go get out of your catalog all the grandma pictures.
Yeah.
You know all these other
Yeah.
things. Is that a solved problem? Is that a
Well,
problem?
no, that's a problem people look at. It's a category search problem where you may or may not have one instance from the category, and you want to see displayed all images that are in that category. There's many, many variations on this thing. The thing that always surprises me, it just amazes me, is that you can get as far as you can with only these things like these color histograms, edge histograms. I mean, when I first heard this problem, my first response was, give me a break. You're going to figure out what image I'm thinking about just by these crude, low-level image statistics? And it's shocking. You can go try the photo book system, the pick hunter system, the one at, what's it called? I can't remember the name of it now. It's a place I work, the system they use. You know, they all have these catchy names, you know. You can go try them, and they're a little flaky. But what always surprises me is how well they work, given that they're using this very, very primitive information. They're not using any kind of semantic annotation.
Well, actually, this is the central thing I was thinking about during your talk, that maybe we think nature is complex and it's very simple. I mean, we know in speech recognition that nobody has beaten trigrams, and it's such a stupid thing, all right? And I was just reading a new paper, very beautiful, by Rani Rosenfeld. He tries to beat the trigrams, and he does, all right? And or we have hidden Markov models, another totally stupid thing, all right? And it may very well be that, in fact, we do, inside us, make decisions on features, on something so primitive
Yeah.
who does just things with features, but maybe it's that way. I mean, Einstein believed that nature is simple, all right, and in physics, in some sense, it's simple, and everywhere we look, anytime we make anything more complex, we don't gain anything. We always kind of the first simple thing, which is sort of right, keeps winning.
Well, yeah. I do know, on the other hand, Fred, though, that if you have keywords, for example, if you use the keywords in just a natural way, just to bias the prior distribution, keep the whole system the same, but just that P0 is not uniform anymore. It's biased by, you need a metric on text, but those are available, a metric on word cross words. But with an appropriate metric on text, and just using that to construct a prior, already you get a tremendous boost.
Well, I just want to say one more thing. I mean, for instance, your example of choosing a picture, right? I mean, that goes in casting, for instance, for film, right? I mean, they want somebody who looks like this.
Right.
They don't have that. They don't even know how they want it to look.
But they know it when they see it or
but
something.
they know it when they see it. And obviously, there would be side information which you don't have. I mean, they say, well, I want a better actor. I mean, you know, we know that this list of actors, you know, but I want a better one, or, you know, or he should be taller.
Right.
So in other words, there would be this side information. Or they are very interested in environment. So they want to know where, you know, how the apartment should look, where they're going to be, where they're going to be shooting. So it's not that it's only your features. Obviously, you want to put in some additional, shall we say, textual information.
Yes.
But I think that otherwise, this is a very powerful, I mean.
Yeah, and the evidence is you can go and just get these systems from the web and play them. I mean, on these image databases, and I find it's very surprising how far
And
you
again,
go.
we have to combine speech recognition actually with image processing, because the instructions you'd like to give to it is, I choose this one, but make it more so and so.
Exactly. That's what you would love. You'd love to have something a little more intelligent than point left or point right. You'd like to have some real, they call it relevance feedback, some relevance feedback, like how about just an English sentence or something, right? That you could then use to make a more intelligent choice of the next display. I mean, that would, there's a potential for real acceleration.